Dear Heavenly Father, we thank you for this day. Thank you for your students in this class, and I just pray for people whose houses and so forth got destroyed yesterday, that you help them out, and just let the local Christian population be able to reach out to them and just serve them this time. In your name, brother Jesus. Amen. All right, so yes, so we have entered the arc of the course. So, I mean, our treatment of modules is kind of exactly backwards to what you typically see for linear algebra. What do you do in linear algebra? You start out with, here's how you work with matrices, and then here's how you solve equations, and then here's an abstract linear transformation, and then we kind of build our way. And in the typical course, if you're lucky, you might see stuff like dual spaces and direct products and internal vector space stuff and all that kind of thing, at the very tail end of the course, if at all. And here, and typically, if you look at treatments of modules, it starts with all the abstract nonsense, and then eventually, in a later chapter, finally gets around to, like, how do you solve equations over modules, and essentially what's the linear algebra of it. So we're now entering the part of the course which is essentially about linear algebra. Matrix theory is abstraction in some sense, but more generally structure theory over a module. And in particular, we're going to be looking at when the base ring is a principal ideal domain. Not all of the results I'm going to tell you today concern just that, but that's where the bulk of our energy will be focused. In not too long. Take that. Yes, something like that. And of course, being discontent with both of the textbooks I've been talking to you out of, I picked yet another one to look at, which is, ignore this graduate text in mathematics, that's just a mislabeling. This is called Advanced Linear Algebra by Stephen Roman, which is, if you want to learn more about linear algebra, this is a great place to look. And so I'll just be stealing from him for the next couple lectures, most likely. First of all, need a little bit of notation. So he does this to distinguish between single brackets, as we'll see. So this is the submodule spanned or generated by a subset of a module M. It's the set of all linear combinations of elements of S. Now, it may not be the case for him, but it will be the case for us that we're going to focus our attention on the ring being commutative from this point forward. All right. I mean, I may say a thing or two about what would happen if it was non-commutative, but for the most part, I'm going to focus on the underlying ring for the module being commutative. All right. So Ri and R, Vi and S, and n greater than or equal to 1. So we're still looking at finite linear combinations, right? So a subset S, a subset of M is said to span M if, or generate M, all right? Here's fine. So he says we use the double angle bracket notation for the submodule generated by a set because when we study the fx module, the v upper tau, we'll also have, so in, let's say, we called it v upper t, we have x equal to, what would that be? Oh, I'm sorry, not x. That's a bad choice. That's the worst possible choice for a vector name, v. So let's see here. This would be just our ordinary f-linear span of v, right? Whereas in this context, what would this be? It'd be something like, if I understand correctly. Well, there's just one V, right? So those are pretty clearly different things in the, you know, the module generated by linear transformation T. And so here I'm thinking, of course, that V is vector space over a field F with endomorphism, right? So my point is that that's the I mean, in particular, there's a place where we would want to use the single bracket versus the double bracket, and you can see the difference.
So the latter is going to be a superset of the former?
Right. Yeah. It is certainly the case here that taking constant polynomials, yeah.
Could you give the concrete example, perhaps, of where it's a strict superset rather than? So not like I can see how it's got to be more stuff like.
Oh, just all you need is that not that V is. You just need that the eigenspace of. I think you just need that the eigenspace of V with respect to T is not. I mean, if V is an eigenvector of V, then fine, these are equal. But if V is not an eigenvector of T, then they shouldn't be equal. Because there should be something in the range of T outside of, you know, linear multiple of V itself. Yeah. Okay, so, you know, so again, the general theme here going forward is we're trying to study the abstraction of linear algebra, right? So one of the questions that you might, I mean, so let's just get some things out on the table here. Suppose you have R1, V1, plus Rn, Vn equal to 0 in such a context, right? He says one very important point to note is if a non-trivial linear combination of the elements V1 through Vn in our module is 0, where not all of the coefficients are 0, we cannot conclude, as we could in a vector space, that one of the, I mean, we cannot solve for a vector. If this is a linear dependence, right? If we have this, where R1 and Rn are not all 0, this does not imply that there exists a Vj equal to linear combo of others, you know. Right. Because we're not working over a field necessarily, which means we can't pick the non-zero coefficient and solve for Vj like we did in linear algebra. To be more specific, here's a nice example that Roman gives. He says in the Z module, Z cross Z, note, here we go, 2 times 3 comma 6, right, minus 3 times 2 comma 4 is equal to 0, 0, right? He says neither 3 comma 6 nor 2 comma 4 is a multiple of each other, right? So that's a kind of neat example for me, because most of the examples I know of, at this point, my intuition is I've spent a lot of time calculating these sorts of things over in algebra, right? Like, here's an example. Hyperbolic numbers, which I use H for. So this is things of the form x plus jy, such that x and y are real numbers. J squared is equal to 1. You could say it's the real group algebra of the cyclic group of order 2 if you liked. But in this thing, you know, if I have, consider my M to just be H cross H, right? Or H2, let's say. I can have things like, you know, 1 plus J, comma, 1 plus j plus 1 minus j, comma 1 minus j, just to give a really boring example. I'm not sure how boring it is actually, but I can make this equal to 0. These are two non-zero vectors, right? They're two non-zero vectors which are definitely not proportional in H2. I mean, can you write, is this a scalar multiple of this? Well, even if you study this space more carefully, you'll find out no. But certainly I can multiply this by 1 minus j, and I can multiply this by 1 plus j. See, because the thing is, 1 plus j times 1 minus j, well, that's equal to 1 minus j squared, which of course is 0, and yet neither of those is 0. Those are the zero divisors in this set. So you see that if I have a vector formed with a tuple of zero divisors, right, then if I have zero divisors as the scalars for this combination, it's 0, despite the fact that I certainly cannot solve for one in terms of the other because, well, zero divisors don't have inverses, right?
It's not only that their sum is 0, it's that each term is individual.
Yeah, in fact, yes, right. That's true. Which is even more disturbing. This does not exist. And so you're right. Each term is individually 0, so I could give an even more draconian example. I could show you that 1 plus j, right? Times, times 1 minus j, comma 1 minus j. Like this is equal to 0, right? In this space. You're right, Sam. That's 0 in and of itself. And so there you go. There's a nonlinear combination. I mean, there's a linear combination of the vector and a constant with itself giving 0. So our definition of linear independence here, by the way, is, well, we called it King's definition in linear algebra for you guys, right? When we have the definition, if S subset of module has, C1, V1, Cn, Vn equal to 0 implies that all the constants, then S is linearly independent in M. Now, again, I'm assuming that M is a R module, and we're assuming the ring is commutative, so it doesn't really matter whether we say left or right, because we can just say it has the standard R module structure. As we discussed, we can make a left into a right and vice versa in the commutative case, essentially just a matter of notation. But for specificity's sake, let's say it's a left R module, all right? And here, I'm not assuming that S has n things in it. S is a set which contains the vectors v1 through vn. The point is, it's a linearly independent set. If you take finite linear combinations from it, look at their linear combination set equal to 0, and if that implies that all the coefficients are 0, that's what we mean by linear independence of a set here. So, with respect to this definition of linear independence of a set, we find the somewhat disturbing statement that the set containing this one non-zero vector, this vector right here, is not a linearly independent set. So singletons containing non-zero vectors are not necessarily linearly independent sets in this context.
So when you say that S does not necessarily have n elements, are you saying that just to allow that S is infinite?
Yeah, S could be infinite. So like we might want to take the set of monomials in, polynomial module or something like that. Yeah. But we always measure linear independence against finite linear combinations because we don't know better. But the thing is, so I've gained my intuition when I look for violations of, my usual intuition for like solving for a vector in terms of the other. I think about zero divisors. How many zero divisors are there in Z though? There are none. And yet we still have this phenomena, right? So you see my intuition's a little bit limited, right, King? I mean, yeah. I guess, most of our examples that we found in our discussions have been based on,
All algebra is just have your divisor and
That's also true. King points out that when we study, so what's an algebra for us, guys? The algebra we're talking about is for me, a real vector space with a multiplication that goes from A cross A to A again. And this multiplication is associative and bilinear. For us, that's a real algebra. I usually take A to be finite dimensional. So in this case, and it's also unital. All right, so because of that, you can prove that such an A is isomorphic to the matrices which represent it. So this is a particular n-dimensional subset of n by n matrices, and then you can do things that you know about determinants there. So like the determinant of anything in the isomorphic regular representation, the determinant's either 0 or it's non-zero. If it's non-zero, it's a unit, because we have a formula by the classical adjoint for the inverse in the regular representation, which we can then transport backwards into the algebra. And if the determinant's 0, well, then it's a zero divisor of the algebra. So, but now I'm getting way off track. Sorry. So my point is that a lot of my intuition comes from studying this more deeply, which is not something as simple as a Z module. It's a little bit more complicated because it's a real vector space, so it's an R module, right? But it's an R module which also has this multiplication on it, which has all kinds of bells and whistles attached, basically. Oh, I'm sorry, no. We don't study the R module structure. I study the A module structure. So I assume that A is commutative for the most part, and so A is itself an A module with respect to this multiplication. It makes it an A module, in fact, and that's where the fun is. All right, we'll get back to that, or maybe I'll write you some homeworks. I owe you guys homeworks. Good grief, I owe you homeworks. I have graded all your tests, by the way, and for the most part, it was good. But then, as I was telling Emily, I've gotten distracted because mid-compiling my linear notes yesterday, my power went off on my laptop. And I don't know what it means. Sam, I need you to look at this file, see if you can resurrect it.
Wait, so it broke this worst tech file?
I don't know how to understand it. My LaTeX file, my text file, is a megabyte. But when I load it in the LaTeX editor, whatever, it shows nothing. It's not cool. And I backed it up a week ago, so I have it mostly, but there's an hour of edits I made yesterday that I think I lost, along with hope of finishing the grading for you guys and handing it back today. So I put numbers on them, but I haven't entered it. And I wanted to grade your extra problem, too, before I hand it back to you. So I'll try to give you everything back Wednesday. Okay? All right. Moving along. So this has a special name. This right here is the cyclic submodule. We can also write this like this. In this special case, with just a singleton, it's also RV, which is RV such that R is an R. But remember, the ring here could be kind of fun stuff, like all polynomials over field, for example. All right, so we know what finitely generated means. We know n-generated means. Linear independence, we talked about. Oh, what's another good example of, this? Here, how about this? The Z module Z. He points out, how about this? 3 times 2 minus 2 times 3 equal to 0. All right. So 2 comma 3 is linearly independent in the Z module Z. So divorce yourself of any hope that primes are linearly independent. Right? Okay, next up, torsion elements. So we've talked about this before, but I will state it again. Let M be an R module and non-zero. So if V, an element of M, is non-zero, and RV is equal to 0 for all R. Oh, I'm sorry. Nope. Too strong. For some non-zero R, then what do we say? Then V is a torsion element. Torsion element of M. All right. A module that has no non-zero torsion elements is said to be torsion-free. With no non-zero torsion. Torsionless. Or torsion-free, right? And if all elements of M are torsion elements, then M is a torsion module. The set of all torsion elements of M together with the zero element is denoted M sub tor in this book. Goodness gracious, guys, I believe that a more common notation for this is tor M. I could be wrong, but I think that's a common notation. There's a functor named tor. Well, it's my categorical ignorance of category. Yeah. Much like the situation with eigenspaces, right? All your eigenvectors and that guy, that pesky zero vector, right? We also, of course, need to think about annihilators. The annihilator of an element, and V, is equal to what? R in the ring, such that RV is equal to 0, right? You can also talk about the annihilator of a submodule, and of course, you could talk about the annihilator, well, I guess a submodule. How would that be defined? I guess it would be R and R such that what? RV equals to 0 for all V and N? Or I suppose you could take the intersection of all annihilators of all elements of N. Right, yeah. He says annihilators are also called order ideals. They have this pesky inclusion. This is a problem you may have recalled doing in linear algebra. It's still true here. If A is a subspace of B or a submodule of B, let's say, that implies that the annihilator of B is, like this. He says, let M be a finitely generated module over an integral domain R. Assume that each of its generators is torsion. That is, that there's a non-zero A sub I in the annihilator of U sub I. Let's see here, he's getting to a point. Well, here's an example of something that has torsion altogether. He says let R be integral domain, all right, and let M be generated by, finitely generated by U1, U2, UN. So finitely generated where each U sub I has torsion. So say A sub I is an element of the annihilator of U sub I for I equals to 1, 2, N. Then if you look at A1, A2, AN, that element, keeping in mind that we're in an integral domain, which is commutative, right? What could you say about this element right here, that's something in the ring that does what? What does it annihilate? It annihilates un, un minus 1, u2, annihilates all your u's, which means by linearity and distributive properties of the ring and the module structure and so forth, that it's going to annihilate everything in M. So this annihilates the whole of M. So you could talk about an M, well, rather, well, an M, this is an element. It has this as an element, right? So what do you guys think about the, what about this submodule? We've spent some time thinking about already the module V upper T, where V is a finite dimensional vector space now, let's say. Suppose it's a finite dimensional vector space. My question is, what can we say about torsion? So let's see, what's our M? Remember? M equals to V, right? And our ring is polynomials in X, which you remember our rule, f of X dot V is just f of T acting on V, right? That's our module multiplication. So we pick a vector in a vector space, right? Pick V in V. So the question is, what would it take for it to be a torsion element? Zero's in there. Okay, great. I mean, tor M includes M, right? Includes 0. So tor, ooh, I capitalized it all of a sudden. Tor M, it just feels right. I know it feels right. Zero's in there. What else? By definition, zero's in there. V in the kernel of Ft. For any, okay, great. I'll buy that. V is in the kernel, if we can find V in the kernel of f of t for any f of x in polynomials over x, all right? So which vectors are those? That does seem like a lot of polynomials to play with. There's a characteristic there's a characteristic polynomial. Good point. So what if we look at that characteristic polynomial for a second? So pt of x is a specific thing, right? It's a0 plus a1x plus da-da-da-da plus anx to the n, right? Ooh, I'm sorry, it's monic, yeah. Remember, we've divorced ourselves from our linear course and found a way to make the characteristic polynomial monic at the cost of lots more minuses in our characteristic equation, right? But we're big boys and girls. And so we can do that. So Cayley-Hamilton theorem says that if we plug in t to that, what do we get? The zero operator on V, right? which means that every single vector in the vector space is in the kernel of the characteristic polynomial. That's one way of stating Cayley-Hamilton theorem, is that when we evaluate the transformation, we plug it into the characteristic polynomial, we get the zero transformation. What's in the kernel of the zero transformation? Everything. So not just zero here. In fact, you see what we got here is everything. So in fact, the V upper T module is pure torsion. Which might go a little bit against your intuition if you're not careful, right? Because we also have the statement that any finite dimensional vector space is isomorphic to Fn, right? Which is, by the way, what's called the free module. We're working our way towards this fundamental theorem of fundamental classification theorem over principal ideal domains, modules over PIDs, which breaks the module into two pieces, into a piece with torsion and to a piece without. So you got to be careful, though. Interpretation matters a lot here. Yes, as an F module, the vector space is free. But as an Fx module, it's not free. It's pure torsion. Yeah. Or you could say it's a torsion module. Okay, moving on. I'm taking some time to tell you that, because as I read on cavalierly my first couple times in Dummett and Foote, I would get on and they would say stuff like, VT is pure torsion. I'd be like, why? Because I think in my mind, I'm still thinking V as an F module. It's my default. All right, moving on. So what is a free module? What's a, let's see here, come on. So we need a definition for a basis, all right? What's a basis? So I think so far, I would say what I've learned today is when making examples, there's two really nice, for me, productive sources to look at. The one is just, vectors built over an algebra, for my favorite algebra, the hyperbolic numbers. But also, Z itself is a pretty decent example generator for these basic ideas. Let's see here. Or Z2, as he used. Yeah. Okay, so definition. M and R module. Basis beta is linearly independent subset of M and right. So it's a linearly independent spanning set is what a basis is. Okay, so yeah, good. Wow, that's different. All right, see here. In our module, M is free if either M is the zero space, the zero module, or if M has a basis. So if beta is a basis for M, we say that M is free on beta. Again, that also is paired with this linear independence and span. Another way we can say is that the module is free on beta. Theorem 4.3, a subset beta of a module M is a basis if and only if every non-zero V in M is an essentially unique linear combination of vectors in beta. Yes, I'm not happy about this term, essentially unique. I'm going to chalk that up to reordering of the basis. Okay. Yes. Theorem 4.4. Let beta be a basis for a module. No, I'm sorry. I guess we're moving. If we have a basis on our module M, then 1, beta is a minimal spanning set, and 2, beta is a maximal linearly independent set. So comment. If basis exists for M, then we can say this about it. 1, beta is minimal. What's that mean? I think minimal means that if you remove any vector from it, it doesn't generate the whole space, right? And maximal linearly independent means that you can't find a set which contains it, a set which contains it and is actually larger, right? It contains a vector outside of the given beta and yet is still linearly independent. In other words, you cannot add vectors to beta without losing linear independence. So join them. So can you think of an example? So here's an example of something that has no, he says the Z module, Zn, has no basis. Since it has no linearly independent sets. I mean, what do we know about anything in Z mod n? I'm assuming Z mod n is his notation for Zn. I know it's a new book, it's a new notation, right? It's part of the adventure. Zn. It's probably too mundane to put in his notation list, right? See, the mundane is the one thing I need in the notation list most forcefully. What if it is? Great, let's look at n, Z mod 3. Using the notation 0, 1, 2, if you don't mind. Actually, I probably should use this for this discussion. The point is that, any number you like times 0 bar plus, how about 3 times 1 bar plus, 3 times 2 bar is 0.
Oh, because 3 is...
The Z module.
0
The Z module. So yeah. Because Zn is an abelian group of order n times anything in it gets me back to 0. Yeah. Uh-oh. Okay, so yes, the Z module Zn has no basis since it has no linearly independent set. But the entire module is a spanning set. We deduce that the minimal spanning set need not be a basis. Zn we can generate by how? Certainly we could say this, right? I think. Is that fair? Yeah. If you take 1 and act on by Z, like n times 1, that's going to build any of the residue classes mod n in this module. So there you go. It's got a... in fact, that's not the only generating set for this. Obviously, you could pick others. Certainly, you could pick any, relatively prime number to 1, for example. And so you can ask the question, so we have a generating set then, right? For example, the set containing 1 is there a smaller set which is linearly independent, despite the fact that, I mean, no. You can't pare anything down to get linear independence because there is no linearly independent sets. Right? So our concept of modification of a basis, of a non-basis to make into a basis from linear algebra is clearly out the window, right? As he points out. He says the next example shows that even free modules are not very much like vector spaces. This is an example of a free module that has a submodule which is not free. So yeah, a free module which has a submodule which is not free. So Z cross Z is free. Z module, right? What's the basis? The usual standard basis, right? 1, 0, 0, 1. Yet, if we look at the submodule, this, right? Z Cartesian product with the 0 set, that's a submodule. You can check it's an abelian subgroup, and it's closed under the scalar multiplication, the Z multiplication, right? So this is a submodule. You can feed it to the submodule test we talked about, all right? You could realize it is the kernel of a homomorphism, right? This is kernel of phi, where what? Phi of x comma y equals to what? Y, yeah. Y. Kernel. You're thinking image. You could also make it the image of the thing you're thinking about. Great. But, well, anyway. No, it's kernel. It's a kernel. Let's just stick with what I've written. Anyway, the point is, it's a submodule. Is it free? Well, no. Certainly not, because can you get a basis for this? So is 1, 0 a basis? Is that a basis? I mean, that's what I might think. Why is that wrong? Oh. Well, anyway, sorry, distracting myself. Oh, in fact, I was wrong. The basis for Z was not what I wrote. This is not it at all. So the basis for this one was actually 1, 1. Let me just think about this for a second here. Oh, I'm sorry. I have misstated it's a free. You see what's wrong with me. This is very bad on my part, but it's a it's a ZZ module. I think Z module, it was actually a submodule. Okay, it's when we look at it as Z cross Z as Z cross Z module. That's where the trouble is. So the thing is, as a ZZ module, we multiply both components at the same way. We don't have freedom to manipulate the first and second component separately. So I don't. Can you guys tell me why that's not a basis then? Multiplied by 0, 1. Thank you, gang. I should know this by now.
So I forget, how did we show these homomorphisms in this case with respect to?
Oh, this is no longer relevant. That was a Z module comment. Now we're looking at the ring. This is a ring, right? And we've agreed that the ring is an R module with respect to the multiplication of the ring. So in that specific case, we can look at Z Cartesian product with 0. That's still a submodule because it'll pass the submodule test. Take two things in there, the difference of things is in there again. And if we multiply by, you know, something in ZZ, it's still in there again. So it's a submodule, but it's not a free submodule because, you know, you can't, anything that you tried to make a basis for it, first of all, the basis has to be a subset of it. So pretty much the basis, you're stuck with things of the form C0 for some C, right, in principle. And in practice, that times 0, 1 is 0, 0, and 0, 1, this 0, 1, of course, is non-zero in ZZ, right? Which, again, is that phenomena I was showing you over the hyperbolic example earlier. It's a singleton which is linearly dependent. Because what we've actually looked at here, this is actually the span. You know, this is, what is this? This is essentially just the span in ZZ of the zero divisor. 1, 0 is a zero divisor in ZZ. So this is not so unlike the example I gave earlier, actually. But, all right, I digress. Moving along here. You can talk about different kinds of homomorphisms. So here's some language for you guys. A endomorphism is what? Is a R-module homomorphism from M to itself. A monomorphism, what's a monomorphism? An R monomorphism, or R embedding, is an injective R homomorphism. An R epimorphism is a surjective R homomorphism. So monomorphism means injective, epimorphism means surjective, and then, of course, isomorphism we know as a bijective R homomorphism. He then talks about quotient modules and the correspondence or isomorphism theorems, which we've already talked about before. Talks about, you know, the complement of a vector. If you have a submodule S and it's got another submodule S prime such that S direct sum S prime is equal to M, then S is complemented by S prime, right? You know, one of the things that we grow to love and understand about vector spaces is that if you pick any subspace in a vector space, you can find a complement to it, right? You take a basis for the subspace, you extend it to a basis for the whole space. Whatever you've extended by the span of those things form the vector space, the subspace complementary to your original S. So there's a well-defined complement to any finite dimensional vector subspace of a finite dimensional vector space. But think about this. If you look at the ring of integers Z, what are the submodules of Z as a Z module? Well, those are exactly the ideals of Z, which are NZ. What's the complement to NZ? What's the complement of like 3Z, for example? You got your 3Z plus 1 and your 3Z plus 2 kind of integers, right? Do those form those don't form a submodule of Z. So see, a submodule of an R module, more generally, doesn't have to have a complementary subspace. So complementarity of submodules is something that we lose in our study of R modules. In fact, he has a list of grievances that he gets to eventually here. And the pages I'm skipping over have theorems about extensions of R module homomorphisms, which we've kind of already talked about. We'll pick those things up as we need in future sections. But here's his list of modules are not as nice as vector spaces. Number 1, a submodule of a module need not have a complement. Number 2, a submodule of a finitely generated module need not be finitely generated. That's messed up. There exist modules with no linearly independent elements, and hence with no basis. Number 4, a minimal spanning set or a maximal linearly independent set is not necessarily a basis. Ooh. Number 5, there exist free modules with submodules which are not free. We just saw that. Number 6, there exist free modules with linearly independent sets that are not contained in a basis. and spanning sets that do not contain a basis. These are all somewhat foreboding comments, aren't they? Because these are all things we take for granted in, for the vector space context. And he says, furthermore, a non-commutative ring may have bases of different sizes. He actually has an example where he builds a basis of size n for a non-commutative module for arbitrary n. So anyway, next up, I will move to his chapter 5, which is on free and Noetherian modules. We'll talk about how the ascending chain condition captures finiteness, finitely generated, and builds our way. So once we have that, then we are one more day on sort of still kind of abstract stuff. We still haven't gotten to the point yet, which is how do we find a basis when we can or can't, and how do we describe that, which is his chapter 6 on modules of a principal ideal domain. I will try to scan the relevant chapters for you guys. I just haven't gotten to it yet. And I've learned I need to do it in sunlight. Because when I do it at night, it produces that like gray, horrible PDF like you saw. Anyway, the one I made yesterday from, that one's better, right? Yeah, good. Thanks, guys.